All right, guys, here we go. Going to get into 4-4 to 4-5, solving some exponential and logarithmic equations and some more fun stuff too. Okay, so looking at this, 2 to the x power equals 16. Okay, so for these exponentials, again, we're going to want to convert this to a logarithm. So again, the key there, remembering kind of our conversion, when we have something raised to a power equaling something else, we can convert that to a logarithm, right? Log base b of y is equal to the exponent, right? So that's going to be kind of our guidance here for the first like 6 problems. Okay, so for this one, right, what we would look for normally is we would look for like, can anything be canceled? Because all we want is this. We just want the base, the exponent, and the answer. Anyway, so we're good. We're good to just convert this to a logarithm. So we can go log base 2 of 16 equals x. Okay. And so again, what that's kind of asking is 2 to what power equals 16? And we know the answer is going to be 4. But again, just kind of showing you guys, we can type that right into the calculator. So if I have my calculator, I can go, again, we want to go math. We want to go down to log base 2 of 16 is equal to 4, like we said, right? So x equals 4. There we go. Pretty simple one to start. All right, number 2. 2 to the 5 minus 3x power, again, kind of hard to tell that that's an exponent, but that is what it is, equals 1/16. So again, it's more complicated because my exponent has this whole expression in there instead of just a single x. But again, I can still convert this to a logarithm, just like I did for the first one. So I can go log base 2, again, that's my base, the thing being raised to the power, of 1/16 equals that expression, my exponent, right, 5 minus 3x. Okay, and so again, I need to evaluate this logarithm, so that would equal -4, okay? -4 is the exponent to raise 2 to get 1/16 as an answer. So it would turn into then -4 equals 5 minus 3x, right? Because that's what this evaluates to. And now this is just like an algebra 1 level equation that I can solve, right? So I can -5, -4 minus 5 is -9 equals -3x. So if I divided, -9 divided by -3 would equal +3. So x equals 3 for that one. Okay, number 3, another similar one, right? Convert to a logarithm. So don't mix these up. The base is the bigger number, and that can happen. So log base 32 of 8 equals x, right? Again, that's another one where I bring in my calculator. Okay, 0.6. So that's it, right? Once I convert this, and I see that that's equal to 0.6, that's it. That's my whole process for that. Keep moving down. 4 to the 7x power equals 2.8. Okay, so again, same thing. Nothing I can cancel, so I just go right into converting. Log base 4 of 2.8 equals 7x. Okay, so I need to evaluate the logarithm, get it down to a number, and then divide by that 7 to solve, right? So log base is this decimal right here. And I'm just going to leave it like that because I know that that would be my decimal. I'm going to divide it by 7. Again, I said you could also round that. You could just say 0.74. You get about the same answer. But if we divided that by 7, then we would get about 0.106, or if I rounded 0.11. So that should be about your answer, 0.11. But again, if you're a few decimal places off from that, it is fine. All right, now we're looking at number 5. We got this e base, right? Hopefully that brings to mind that's our natural log, right? Natural logs also is the same as just, well, log with a base e, right? But we just write natural log instead. So we're going to convert this and say natural log of 7 equals 5x, right? Because even though it's a natural log, it still follows the same rules, except we just don't write the base of e because that's implied with a natural log, right? So I'm going to evaluate natural log of 7, and then I would end up dividing it by 5, right, with that 5 there. So natural log of 7, that's just this natural log button right there, right? So natural log of 7 is 1.9459, and then I divide that by, whoop, it still has my answer saved. I divide that by 5, and I would get this decimal of 0.389, convert round it up to 0.39. There we go. So again, natural log of 7, divide that by 5. Alrighty, looking now at number 6. Now, we said that if we have x's on both sides. We cannot just do the simple convert to a single logarithm, evaluate, and solve. Okay, for this, I'm going to bring another piece of paper because it's going to be a longer problem. I can't do that. Okay, I need to do something else. So what I need to do is I need to do the logarithm of both sides. Okay, because that's a logarithm is how I cancel out an x in the exponent position. So again, I'm going to end up taking the log of both sides, right? Because a logarithm is just like any other operation that I can do to both sides, like adding something to both sides or subtracting or whatever, right? But I need to choose a base, right? And you could, like when we write just log like this, that's implied that it's like common log base 10, right? What would be more helpful, maybe save me a step or two, would be to choose one of these values as a base. So if I just chose 4, because what that's going to do is when I evaluate this later, that's going to make one of these cancel out really nicely, okay? And then what I can do from here, right, is apply that power rule, right? What that says is I can take, when I'm taking the logarithm of something with an exponent, I can take that exponent and bump it out to the front as a coefficient, right? So those are my logarithm rules that we learned. So I do that, right? So it's rewritten as x plus 4 times log base 4 of 4 equals 2x plus 5, that other exponent, times log base 4 of 5. So that's my first two steps. Log both sides, apply that power rule. Okay. And so now I got my groups with my x's. And again, it's helpful because now they're not in the exponent position. I can actually solve for these x's, but I need to evaluate these logarithms now. And I can do that too using my calculator because they don't have x's in the exponent position anymore. Okay. So I can go in, you should hopefully know this, but log base 4 of 4. So that's again asking like 4 to what power equals 4. Now just be 1, right? That would just be 1. So that is going to turn into a 1. And I'm going to do the same thing, log base 4 of 5, and I'll get a decimal about 1.16 or 1.161 if you wanted to be precise. Again, this evaluates to 1, right? And that's going to be multiplied by this x plus 4 group. And this group stays for now. And again, this right here evaluates to about 1.16. Okay, I'll just leave it like that. And now I don't have any more logarithms or x's in the exponent position to deal with, and I can just solve for x. Okay. So again, I would distribute, right? But distributing this 1 doesn't change that. It's going to stay x plus 4. Now distributing this 1.16, okay, so 2 times that would make this 2.32x. And then plus 5 times 1.16 would end up giving me 5.8, 5.8. Okay, so now I have this, and again, all I'm trying to do here is just get x by itself, right? So all the x's on one side, all the constants to the other side. So I'm going to minus this 1x, right? So that would make it 4 equals 1.32, right? 2.32 minus 1, 1.32 equals that plus 5.8. I don't know why I'm having trouble with those 8s. But then I would subtract that 5.8, right? So 4 minus 5.8 would equal negative 1.8 equals 1.32x. And then lastly, I'm going to just divide. Negative 1.8 divided by 1.32. And I get an answer of negative 1.3636 forever, right? So x equals negative 1.36. Okay, so there's my answer for number 6, negative 1.36. 7 through 10 here on the front. We are now going the other way. I have a logarithmic equation, and I am going to solve. But again, notice where the x's are. Okay, for when I converted these to a logarithm, my x's were my exponent, right? So my x ended up being over here. Okay, so now for these ones, my x is not the answer to the logarithm, my x is over here. So if I converted this to an exponential, let's do that. So I would have, again, kind of using this guide up here, right, my base, my answer to the exponential, and my exponent. Okay, so 2 is my base, 5 is my exponent, x is my answer to the exponential. Okay, and so again, if I just do 2 to the 5th power, or 5 2's multiplied together, I would end up getting 32. Okay, so when the x is in that position, it's easier to answer it when it's an exponential. And so that's what we're doing here. Okay, but the same rules apply here. I want to cancel everything other than my logarithm and then convert it and solve. Okay. So number 8, log base 6 of x plus 3 equals 2. So I would still just write 6 to the negative 2 power equals x plus 3. Okay. And then again, I can do 6 to the negative 2 power to the negative 2 power, right, using my caret button there to get up to negative 2 exponent. And I get negative 2.78, let's say that. X equals, well, I guess, sorry, it would be negative 0.02, I'll just say negative 0.028 equals x plus 3, right? Because that's what this evaluates to. And then I can just minus 3. So x would equal this minus 3 more would take me to negative 3.028. So that is my answer for number 8. All right, a couple more of those, and then we're moving on to other problems. Okay, so number 9, 3 plus 9 times the natural log of x equals 0. Okay, so now, right, when I convert this to an exponential, I want it to be just the logarithm on that side, right? And so I have these extra values that I want to cancel first. So I'm going to minus 3, 9 times natural log of x equals 0 minus 3, negative 3. And then I can divide by that 9, right, to cancel that. So I'd be left with natural log of x equals, right, you could say negative 1/3, or you could say negative 0.3 repeating, right? Okay, so now converting this to an exponential, right? Remember, natural log has a base of e, so that would be e to the negative 1/3 power equals x. Okay, and don't forget, e is a value, right? And using your calculator, you can evaluate this just as easily as you would have evaluated like 6 to the negative 2, right? This is going to give us a single value. So I can go in, right, e, I can go second natural log e to the, do a fraction, negative 1/3. And I would get about 0.72. Okay, so x would equal about 0.72 as an answer there. Okay. For this one, okay, I have 2 logarithms with the same base. So that's helpful that they have the same base. So what I'm going to do here first, right, is when I have 2 logarithms that can be written as 1, right, because I need to have them written as 1 so that I can convert it to the exponential. Again, with where these x's are, we see that it's going to be helpful to write this as an exponential. But I can't do that with these 2 separate logarithms. I need to write it as a single logarithm, right? So that's what I want. And so we think, okay, how could I do that? Well, that, you remember your product rule says that if you have 2 logarithms that are written that have the same base that are being added, I can write them as a single logarithm, right? With these 2 things that I'm taking the logarithm of would be being multiplied here. So that's what the product rule says. It can kind of go both ways, right? I can write this and expand it to be written like this. But in this situation, I want it to be written as a single logarithm like this. From here, again, you're going to have to distribute this x at some point. So let's just take care of that now. Log base 6 of x times x squared. X times negative 35 would be negative 35x equals 2. Okay. And now that it's written like this, I lied, I'm not going to use my other piece of paper. I can convert this, right? Everything, there's nothing I can cancel, right? So I can convert this to the exponential. So again, that would be 6, my base, squared, my exponent, equals this group, x squared minus 35x. And so now I look at this, right? I can say 6 squared, that's just 36, right? And then from here, I want to solve this, right? But you see that there's an x squared involved. So this is going to be a quadratic, right? And so what we want to do with a quadratic, right, it's kind of the opposite of solving normal equations where I want the x by itself. With a quadratic, I want all the values on the same side. So I would minus this 36, kind of put it on the end of the other side. So x squared minus 35x minus 36. Okay. And so then now we have this quadratic, right? And so you have 2 options from here. You can either use your quadratic formula program that you guys have in your calculator and solve, or my preferred method, you can always factor, right? If you know how to factor. How can we write this in 2 separate groups? We can say, right, this would be what multiplies to get negative 36, adds to get negative 35. It's got to be x minus 36 and x plus 1. These 2 numbers multiplied equal negative 36. These 2 numbers added equal negative 35. Okay. And so again, using our zero product property and kind of skipping some steps, I can go from here, and the value that I'd get from this group would be x equals positive 36, and the value that I'd get from this group would be x equals negative 1, right? I would get those because I'd set each group equal to 0 and kind of do the opposite, okay? But we're not quite done here, right? I shouldn't have circled both answers because we said too, not both of these answers would work, okay? The only one that would end up working out well would be the positive 36. The negative one would not work, okay? Because look, log base 6 of x. If I substituted in negative 1 in for x there, right? So look, and my calculator actually gives me a value, but it has an I in it. You see, a lot of the times the calculators don't give you an answer there. It'll say error, non-real answer, okay? But this is also a non-real answer because it has that letter I involved. And so we're not dealing with answers here. Or we're not dealing with non-real answers. So yeah, this would be a no solution answer. That would be a non-real answer, that's called. So the only value that would work would be a real answer would be this positive 36. All right, guys, on to the second page here. I'm looking at these compound interest and exponential growth and decay type problems. All right, so first one's asking, find out how long it takes a $3,200 investment. So again, just kind of reading through, that's going to be my P, my principal, to earn $400 interest if it's invested at 9%. That's my rate, compounded quarterly. Okay, so that tells me that my n value is going to equal 4, and the fact that it's compounded quarterly means I'm also going to use this first equation, not my PERT equation. Okay, and again, with the rounding, this isn't going to be on the test. Don't worry about necessarily doing the right rounding. Now, the only thing that I'm missing, right, and it's what am I solving for too? I don't know how long it takes. That's my time. I don't know how long it's going to take. Okay, so my t is going to be my unknown value. But that means that, right, I have my principal, I have my rate, I have my n value. I don't know this a. That's not told to me clearly. But this $400 interest, okay, means that along with the $3,200 I invested originally, I have this $400 interest added on to that, right? So that would take me to 3,600, right? So that, again, not told too explicitly there, but that's 400 added onto that principal would be my final value. Substituting the rest of it in here. Again, t is my unknown amount. Okay, so I start this out by, right, dividing by the 3,200. All right, so I think that would give me 1.125. All right, so I divided, I got 1.125. And then from here, right, what would help is if I simplified this into a single value, okay? So if I did that in my calculator, that would just over 4, so about 1.0225. Okay, not necessary to have all those decimals, but again, the more that you include, the more accurate your answer. So let's keep it like that, 1.0225 to the 4t power. Okay, so I canceled everything I can, I simplified, and now I would want to convert this to a logarithm, right? So it's this different base, so I'm going to do normal log of 0.0225 of my answer there, 1.125 equals 4t. Okay, so I have that, right? And then I am going to take that logarithm and then divide by 4 for my answer. So that gives me about 5.29. And then I divide that by 4, and I get about 1.32. So t is 1.32 years. So that's how long it would take this to earn $400 interest at that rate and that compounding. Okay, so about 1.32 years. All right, next one. Cindy will require $20,000 in 4 years to return to college, blah, 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 blah. Okay, so continuous compounding means that it's our PERT equation. And now this one's tricky, so just kind of getting your head around this scenario. She needs 20,000 4 years from now, okay, which means that this isn't our initial amount, that's her final amount. That's going to be A, okay. So we have our time, we have our final amount, okay, and we have our rate. We don't need that compounding amount because it's continuous. But what I don't have is this P. Now, I don't think we've done one like this in class. Maybe there was one on the homework that I'm forgetting about, but so 20,000 is our final amount. She's being nice to her parents. She's saying, hey, don't give me exactly 20,000. I want to be nice to you, save you guys a couple $1,000s by taking an amount of money now, investing it so that it is 20,000 in 4 years. So Cindy wins Daughter of the Year for doing that. So putting the rest of this in, right? So we have 20,000, we have PE, we have our rate, we have our time, 10 years. Okay. Now, normally, what we would need to do in this case, right, because normally one of my variables is either my rate or my time, I would need to take the natural log and do all this. Okay, but don't forget, e to a number power is a value. We can find an answer for that, right? So if I took e, second natural log, e to the 0.1 times 10, and again, that would be exactly what e is actually, right? Because 0.1 times 10 would just be 1. So e to the first power is just itself. So let's just say it's that 2.7183, if we round just a little bit. So P times 2.7183, or pretty much exactly what E is. So basically my answer is going to be 20,000 over E, essentially, is going to be what P is equal to. Or again, you can round it and get that decimal, that's fine too. So P, if I just did that, 20,000 divided by, again, E if you want to be exact, or you can go with that decimal if you rounded, about 7,357. So how good is Cindy? She's saying, hey parents, if you give me 7,357 and if I round 59 cents, now I can invest that at 10% interest, compound it continuously, and it'll turn into $20,000. So way to go, Cindy. Okay, next one. Larry has $2,300 to invest and needs $2,700 in 10 years. Again, so a lot given to us there. He has this now. That's his principal. He needs this later. That's his final amount, and that's his time. What annual rate of return, so my R is going to be my variable that I need to solve for, if his interest is compounded continuously. Okay, so not having an end value again, we're using our PERT equation again. PERT would be our kind of our standard equation, but again, substituting in the values. So $2,700 equals 2,300 E to the R times 10 power, right? R is our unknown amount. So again, solving this one's more like what we're used to, right? We divide by this coefficient, 2,300, it's about 1.174 e to the 10r power. And then now, right, now I need to convert this to a natural log with that e base, right? So natural log of 1.174 equals 10r. So I'm going to take this natural log and I'm going to divide it by 10 to get my rate, okay? So natural log of 1.174. Or I could, again, if you want to be exact here too, let's do that. We can divide by, or we can take our second answer. Okay, that's another way. If you want to be the exact, if you don't want to round and get a more exact answer, you can do that. Again, either way is fine. On the test, I will account for both of those. So natural log of 1.174 is 0.16, and divide by 10, 0.016. Bump all those numbers over one place, right? So about 1.6% interest rate, about 1.6% rate would get us there, get him to that $2,700 that he needs. Okay, 14. The half-life of silicon 32 is 710 years. You guys remember half-life. Half-life is, that's how long it takes for half of that thing, that element, or whatever it is, to decay. If 100 grams is present now, how much will be present in 100 years from now? Okay, so again, this is our, we think about our, again, very similar to PERT here. We have our kind of exponential growth decay equation dealing with our final amount, our initial amount, my decay rate, and my time. Again, this decay rate's always going to be negative. So again, for this problem, guys, we are told that the half-life is this, and we are given these times. Now, what we're missing here, so we're going to have to do this in two parts. We're going to have to find K, our decay rate, using this information about the half-life. And then we're going to use that rate to then solve and answer this question it's asking. So finding K. Okay, so the half-life, which means, again, the 50% would be our final amount. 1 or 100% would be my starting amount. And then my rate's unknown, but the half-life is 710 years. Okay, so that's what I know. And then from here, I can go, and again, I would divide by 1, but that doesn't do much. So pretty much I can just go right into saying natural log of 0.5 equals 710K. And so my rate, my decay rate, is going to be found by doing natural log of 0.5 divided by 710. Okay, so if I did that, natural log of 0.5 divided by 710, I would get, again, you get really small decimal. Again, this does not mean 9.76. This means this, but move the decimal point 4 places over to the left. Okay, so the K, my decay rate would be equal to, again, I'll write how it is in the calculator and then how you convert that. So about 9. And then, again, but that's times 10 to the negative 4th. So if I bump that over 1, 2, 3, 4, that would end up being negative 0.00099763 would be my decay rate. So again, that doesn't answer my question, but it does give me the information that I need to answer the question. So what is this asking? It's asking if 100 grams is present now. So that would be our A of 0, our starting amount. How much will be present? So we're solving for the final amount. We're not going to know this A, okay? But I know my decay rate now. I know my starting amount, and it's giving me my time here too of 100 years. So substituting all that in, so 100 grams, e to my decay rate times 100 years. So there it is. And then again, I can go in and look, all this is nice. So I can substitute all that into the calculator. Okay, so I get about 90.698 as my answer. And again, what does that number mean? That number means that about 90.7 or ish, that's how much, again, always look at the question at the end. That's how much will be present in 100 years. So 90.698 grams of silicon 32. All right, last one of these and then on to the last page. So a fossilized leaf contains 11% of its normal amount of carbon-14. How old is the fossil to the nearest year? Okay, 5,600 years is the half-life. Okay, so with this, again, kind of the same as the last one. I'm not given a decay rate. Again, don't be deceived. This is not a decay rate. That's how much is left after a certain amount of time. So we need to find K, same as the last one, and then use that to answer the question. The question here is going to be for T, how old is the fossil? So finding K, again, using this information about the half-life. So 0.5 equals 1e to the, again, my rate is what I don't know. My half-life time is 5,600 years. Again, so I know that, and I can just go right in. Natural log of 0.5 equals 5,600K. Then I would divide by that 5,600, right? Again, so I can do that. All right, so I do that, and I get, again, another small decimal. But again, this means bump that decimal place over 4 times to the left. So that would be, K is going to equal negative 0.000124. We can round that up. Okay, so again, that's not my answer, but that is my decay rate that I need to answer the question. So again, what is it saying? It's saying 11% of it is around now. So again, that would be, even though that's a percentage, we can still use that as a final amount, kind of thinking in terms of percentages. So 11% is my final amount, and that's assuming that 100% of it was there at the start, right? That's 100% is the starting amount of that carbon-14. To the, again, I know my K value now, negative 0.000124 times T would be, again, my unknown value. That's my variable, right? How old is the fossil? So again, here I'm going to need to use natural log too, but it's going to be natural log of 0.11 equals my decay rate times T. And then again, calculator comes in to save the day because that's a really hard thing to do. 0.11 divided by negative 0.000124. And I get 17,800.60. 17,800.6 equals T. And so again, what is that? That's the number of years. That's how old this fossilized leaf is. 17,000 years old. Very good. All right, guys. That is the second page. Keep on going. Third page here, the extra problems. So 16, what interest rate is necessary for 5,500 to grow to 7,000 if you were to earn monthly compounding for 10 years? Okay, so just all one sentence gives us everything we need. Original amount, final amount, monthly compounding, so the n is going to equal 12. And then 10 years, that's my time. So again, solving for R, solving for rate. Okay, so again, my first equation, 7,000 equals 5,500 times 1 plus, my rate is unknown, my n is 12, 12 times 10 years. Okay, so then again, doing this, I can divide by my coefficient. So 7,000 divided by 5,500, 1.2727 repeating. Again, I have this, but I can't condense this down into a single thing because that's where my variable is. Okay, so again, this is another one, kind of, we did one of these in class where I have this, like if I wrote 12 times 10, that'd be 120, right? So you have a couple options. You could either take the 120th root, right? Because my variable is not in my exponent position, so I'm not going to need to do a logarithm here, okay? But I need to get rid of this exponent so that I can kind of unlock this r and I can solve for it. So what I need to do is cancel this out. So you can either, it just depends on how you type it in the calculator. It's either do the 120th root, or you can raise both sides to the 1 over 120th power. But it needs to be to both sides, right? So I need to do 1.127 to the 101 over 120th power. And so we get this super small 1.002. So that's not too bad, right? And now this exponent's gone. All that I have left is 1 plus r over 10. So now I need to subtract 1 and then divide or multiply by 10. So subtracting 1 from this will give me 0.002 equals r over 10. And then multiplying that by 10 would move the decimal point over 1. So my rate ends up being about 0.02, or again, that would be about 2% rate. 2% rate needed to grow from this to this in 10 years, monthly compounding. Okay, last one. This is our logistic growth model, okay, dealing with this kind of inverse equation. And so this is the population of planet Earth in billions can be modeled by the logistic function there, where x is years after 1949. Okay, so what was the population of Earth in 1949? So again, that would be plugging in 0 for x, right? So that's because that's kind of our starting year. So if we did that, 11.82 over 1 plus 3.81 e to the negative 0.027 times 0. So what's nice here, e to the, this times 0 is 0, even though it's a negative, it's still 0. E to the 0 equals 1, okay? So basically this is all going to go away with that, 0x. So 11.82 over 1 plus 3.81. Again, and we could say times 1 there for the e, but so basically I need to just figure that out. So 11.82. So 11.82 over 1 plus 3.81. And I get about 2.4574, a couple decimal places. 2.4574. Again, that's not how, you can't have 2.45 people, but it's billions, right? So that was about the population of Earth in 1949, about 2.5 billion people, or a little bit less. And okay, according to the model, what was the population of Earth in 1980? Okay, so guys, now, and I didn't graph this yet, but again, let's graph this in the calculator. Let me type this in. And again, we talked in class 2, so here, like, if you just type in for y equals, and you hit graph, right, you look at something like this. We want a better view of it here, right? So let me adjust my window. So you see, I chose a window. I'll show you after this is done. I chose a window of 0 to 400 on the x, 0 to 15 on the y. Okay, and that gave me a pretty good view of it there, right? And yeah, so if it's asking you to sketch the graph like it is, so we're going to go out of order here. Let me graph C. So I went from the x-axis from 0 to 400. It doesn't have to be exactly that, right? You could probably have gone to 300, and you just want a good view of when it flattens out like that, right? So 0 to 400, and then from 0 to 15 on the y-axis. And again, guys, use this value up here as a good reference point for, because that's going to be the highest y value that it goes to. I go like that. Okay, something like that. Probably doesn't look quite like that, right? Obviously, I should have drawn my curve a little bit earlier, but you get the idea. So there we go. That's as much as we need. Okay, if you want to include points in here too, but we talked about how you don't really need that. So according to the model, what was the population of Earth in 1980? Okay, so we need to figure out what x value there is it talking about. How many years after 1949 is 1980? So the simple subtraction, 1949 subtracted from 1980 would give me about 31 years. Okay, so I want to figure out when x is 31, what is y equal to when x is 31? Okay, so again, I can go second calc value and type in when x is 31, what is y? So I see when x is 31, y is about 4.461, and that would be, again, billion people. So that was the population of Earth approximately in 1980. Okay, according to the model, what will the population of Earth be in 2040? Okay, now that I drew my graph, again, don't need anything fancy there. So again, how many years what's my x value there? So that would be what, 91 years in 2040 after this. So again, same thing. We can go second. So second calc value 91 years. When x is 91, y is 8.91. And again, that's billion people. Okay, it's pretty simple. And now this last one is changing it up on us. It says, when will the population of Earth reach 8 billion? Okay, so again, we need to figure this out. And we need to say, okay, it's giving us when y is 8 billion, what is x? So this is a little bit different. So what we need to do is go into our calculator, okay? And unfortunately there's no calc for given a y value finding x. So what we can do is just take the y value that we know, so that's 8, okay? So what that's going to do is give us a straight horizontal line, okay? And what we can do is calculate, okay, that intersection point, okay? When y is 8, what is x? We can go second calc intersect and kind of scroll over till we get to that point. Okay, so scroll over there. It's asking where is it about on the first curve. It's right there. Second curve about right there. Guess, I don't know why it does that. So intersection, okay, so when y is 8, x is 76.919 or 76.2. 76.92. And again, what is that? That's the number of years after 1949. So I can go 1949 plus 76.92. You can round it up to 77 even, because it probably will want exact years. So let's see, we'll get our answer and then round up. So that would be about 2025, 2026 if we round it up. So not too far from now. So 2026, they're approximated based on this model. That's when the population will reach 8 billion. All right, very good, guys. So that is the review. Thanks for following.